Shall I start? Yes. Okay, so I think the first thing clearly is do a little bit of translation, okay, between my notation and notation of David. So because and I said you could be a bit confused. This is why I managed to save this part of the black one. Unfortunately, that part was too late, so it was already erased, but I will rewrite it. So you see clearly this. I hope you understood that what I introduced yesterday was this compensator field. Okay, actually, if I want to have it, that form will be the U dagger that was transforming as G left U dagger, and I call it here H. Okay, that's exactly this psi. Okay, so this is the psi. So why I call it compensator? Because it compensates, if you want, a transformation which is transformation belonging to the vectorial subgroup. So this is an element of the SU3. Okay, but indeed we put here an X, and this is why David called it U, because we consider SU3 left plus right transformation, but in the general context where we are also making. So if you want, this is an element of this group, but we are doing a full transformation under SU3. So when I do a transformation under the full group, okay, I get this nonlinear transformation, which however is an element of the vectorial group. Okay. If on the other hand, the transformation is really only of this group, this becomes what I call the little h without dependence, which is what here is called W. You see the difference is that I can do a generic transformation here. Okay. If I do a generic transformation here, okay, something like a baryon, so the baryon, generically, no matter what, the only things we know is that transform like this. Because nature is telling this is an octet. We know this, the symmetry, this is a good symmetry of nature, okay? So it has to have a well-defined transformation property under this, and this is the transformation, which actually, if I really do the transformation only under, this is the transformation under G, okay. And this is the transformation under, so this is the power of this Cullen-Coleman-Zumino best formula. It's telling that if you use this variable, this U and H, you get this representation that can allow you to interpolate between the two. So becomes a linear representation when you restrict to the H group, and become a non-linear one when you are in the full group. Okay. And this compensator field is the one that really allows to compensate something that transforms under, which has well-defined transformational property under H, and make it something that transforms with well-defined properties under the G group. Okay, this is why indeed at the end we can, so this is the key equation, okay? Like the other key equation was that sigma was equivalent to my little u, which right? So these psi or u are these compensator fields, which are really important if you have something that you know how it transforms under H, and you want to build out of it something that transforms under the chiral group. So if I take my baryon, then a combination of baryons plus pions can transform either as left-handed or as right-handed or any type of things I want, provided I do the right combination. Okay. And indeed, the other things that were erased, there were these A mu and V mu, which they introduced, which right, this is what was written, not part of the Blackboard, right? Now this, if I use my notation, you see this psi dagger becomes, this becomes U. Which actually is the same thing, okay? And is what yesterday I told you was, I call it gamma mu. Is the things you need to build the covariant derivative, okay? For instance, of the barrier. We have seen it before. And A mu is something which is, on the other hand, okay, let me just, I could do it with xi, but just for, let's do it with the, let's do it with the U. So this is U d mu. U dagger, okay, just writing here. Now this term, you know, I can put the covariant derivative, the derivative here, because derivative of this is 0, so d mu the dagger psi plus d mu. So, sorry. Right, and this is true also for the U, because this is just one, right? Which means that d mu psi is equal to, if I move the derivative from here to here, I change sign. So this, I write it as plus. And now this will be d mu U dagger, and this will be U, right? I just rewritten this term here. I move the derivative here, and then I change the name to U and U dagger. Now let me rewrite this term. Let me add U dagger U, which is 1. Plus here, let me do like this. So what I want to do, yeah, let me do here. I think I made a mistake somewhere. So the first one, this is like this. Okay, this is, I just, so this is U. This, because I put here U dagger, right? I just insert this unit term here. Because now look, what I have is U, and then you see here I have this term here, and this term here, which is not the derivative of the big U. Because U dagger U, it's U. So that is what I have. So that is my, that is the object, which now you see that this is now understand very well the transformation property of this object, because we know how this transform. So this now transform linearly. So this we know that transform under transform as G light. Right? And then with the appropriate compensator, I do something that then transform under the vectorial group. Right? Now this term, if I look at how it transforms, well, the transformation property is transforming. So this derivative now acting on something that transforms linearly, it's just a plain derivative. Will not, the derivative here doesn't matter, because these are global transformation. So this now transform, remember U transform into G right. Sorry, here I want to use the fact that U transform as H dagger, U G left dagger. So these things will compensate my G left. And here I have this term that goes like G left, D mu U. And then I have my G right dagger. Here my U also transforms as G right U H. So this will go away. And so this will be H dagger, my object H. So I have a nice object we transform as H dagger H, okay, which has the property of being an axial current. So it's nothing but our d mu u. Okay, there is nothing u, but we compensated with compensator field to get something that transforms like this. Okay. No, this was a mu. V mu is this other object here. So a mu is these things which I've rewritten here. Okay, so yes, I mean, so this because I moved the covariance, so this is plus. Yeah, that's what I did there. So I can write both with the plus. The V mu it's different. So V mu is this object here, which on the other hand really transform with the derivative acting on H. So here you cannot get rid of the derivative acting on H. And that is why it's important for the covariant derivative. Small u transform as, so little u transform as G right u H dagger, but also as H u G left dagger. Yeah, H, sorry. Sorry, thanks. The black one looked a lot. Sorry? Thanks. Okay, so as it should be, there is H dagger should be on the right side, on the H on the left and H dagger on the right. Thanks. Okay. Is that all clear? Yes? Here, you mean? So the point is that, so the B field, when I act only on H, transform linearly, okay? If I act on H, is a subgroup of this, is a subgroup of G. Now, if I act with the full G, then Vestumino told me, look, what will happen to B when you act with the full G is that you have a nonlinear, okay, representation of the group, which is this one, the one that we derive with the CCWZ formulas, which reduce to linear only if you act on the specific subgroup, which is the unbroken one. So which means this is still an element, you see, this is still an element of H, but it's an H-dependent element, which depend on your pion coordinate. Because now you decide to explore the full structure of G. So you're not only doing, so this isn't them doing a transformation under the big G, the big group, okay? Under the big group, this still, remember that actually when it was under H transformed linearly, but remember in this non-trivial way that is now the transformation property, it's an element, but now it's an X-dependent element. So it's really, this reduced to this only when I look at a subset of transformation. Okay, but thanks for the question. So it's subtle, okay? But it's very interesting, very, very rich structure. And again, the fact that we know, you see, again, there was also a question last time. If we only look at this, we are stuck, so we can build many operators. The power is that we know that the full theory is invariant under that. Okay. And then once we establish how all the things transform, we really look at transformation property under this big group. Okay, so if that is all for the translation, let me erase that, or maybe I can start from that. We will erase it later. Maybe just a comment I want to make, because indeed we have this nice discussion about the quark masses, huh? And again we will come back on it a little bit. In the early days, when Kerr perturbation theory was formulated, also there were not lattice results, so it was not there was this Gell-Mann-Okubo mass formula. It's known since a long time, and it works very well. And actually, this is a consequence of the fact that we have these pion masses, kaon masses expressed linearly in the quark masses. Although at that time was derived not just because of the quark masses, it was derived just because assuming small SU3 breaking. Sorry, small isospin breaking versus SU3. There was at some point and in the end of 80s, beginning of 90s, people started to think maybe, but it's not obvious that the quark mass square are negligible, okay? So who tell us that, so the counting, so why we should treat the quark mass? So maybe it could be an accident that the pion mass and the kaon mass seems to be linear, but actually maybe it's just a cancellation, then the quadratic terms are important. Then there was an alternative theory where there was a different power counting, where the quark masses were counted different, such that the leading term was the quadratic term. And finally, this gives rise to prediction, which have been falsified, and now there are lattice results. But again, it was not obvious, okay? And again, it's not, this is something that it's a property of the ground state of QCD that surprises us. Okay, so what I want to do today, okay, well, first is to come back a little bit to our general formalism, and then go on. So you remember the idea is to consider this generating functional from the QCD side. So this really is QCD with 2 or 3 flavor, 0 masses. With this is why I call it L0 QCD. And then we add these external sources. Okay, you remember we were there. So for me, this J is the full set of L, R, and S. And the idea that we want to build a representation of that via the chiral field, okay? And so which, sorry. And what I already told you at the end of last lecture, so indeed we have seen what is these things we will expand it in power of operator containing more and more derivative of more and more quark mass term, and we know the leading term. Now, I introduce something which is, again, to confuse you even more about notation. So now for the quark masses, I do something slightly different, but it's absolutely the same, of course. Again, I stick to the European notation, which is this one. So I introduce this. So here, I introduce this chi. Let me do it immediately right away. So this chi, it's for me something which is an unknown constant, which you will see this is really equivalent to what David called lambda tilde, the one that entered in the quark masses times my source S. So this is it has to have a dimension of a scale, because you see these terms here I put F square as David also did. Then I have this chi, so this has to have dimension 4. So here there is S which has dimension 1 because it's a scalar source coupled to a current which has dimension 3. So then this B0 has to have dimension of a mass, and it will be our lambda. And then I want to derive an interpretation of this B0 in terms of a green function that we can like we did in the case of f pi. But just to remind you on the other hand, so what we did here, so this d mu, okay, as also you have seen today, this is, I think yesterday I had some wrong sign, so let me do it correctly. And we derive this using this trick of promoting the transformation property of L and R like this. See, adding this term, okay, I get something that here it's at the QCD level, at least at the classical QCD level, because then we will see there is the anomaly. We'll come back to that. We see that this Lagrangian is invariant under this transformation property, okay, even including this term, because these are the neutral current associated to this transformation, and therefore, basically, we deduce, we have the same structure here. So basically, this you can absorb in this way you can have a covariant derivative, with respect to your quark field, which are here, and you do the same thing here for your meson field or U field. Is this clear? And this way, of course, for instance, if you want to introduce photons, you can choose this to be A, okay, but you can also do something else. Now, what about this term here? And also we have seen, remember, we have seen yesterday at the very end that looking at we were able to identify this relation. Now, there is one point I want to comment that, so here people correctly question the fact that, okay, if I really do look at this will give me the expectation value of this object on the vacuum, right? And not on the state of a pion. So how I get the pion here? So here, let me open a parenthesis. Well, formally, to really get to get the pion here, so it's true that when you have your generating functional and you look at this, will give you the vacuum expectation value, okay, of a certain number of an operator. Well, yeah, let me say, yeah, let me do it general. Now I'm doing just a generic theory, okay? So I put an operator here. I have my current. Okay, and then if I do my, with respect to J, and I set J equal to 0, this will give me the expectation value of X, right? This we all agree. So this one is the definition of the path integral formulation. Now, if I want to get these things here, what I need to do in my theory, okay, now I go to my full theory. So my QCD Lagrangian, so this will be QCD. Then here I have my J associated to the actually, QCD, sorry, this will be QCD. Sorry, so this will be my L mu. And this is associated to this curve. But then I need to put something else, like I will put O pi x, okay, and another source, let me call it. So this operator is the operator that I need there to create a pion. Okay. So then what I will do here, I will do a. So I'm adding an extra term here, which has to be a source for the pion field. Okay. Then what I do is the second derivative with respect both to the current I'm interested in and to this pion field in a different position. Okay. And now this will give me the time order product of my Q bar to point X and my, that is the thing, okay? Now I can choose, you see, these are two different positions. Then I can choose my point where I create Y to be far in the past and finally, and then insert here a set of states. So this will be, what this operator will create a pion from the vacuum. Okay, actually I put in the operator to create the pion from the vacuum. So then what I will have here is and then so these things will create the pion state on the vacuum. So here I can insert a set of intermediate state. We call it N. This is the identity, and this will give I pick it up such that this will give a leading contribution when this is the pion. Okay. So finally, this is just the propagator of the pion, and basically all these things will be dominated by something which is related to the wave function of this operator, how it creates the pions, something which I don't care because I will do the same thing both here and here, and then we'll cancel, we'll drop. Okay. Actually, this is how it's done on the lattice. So on the lattice, you put a source to create your pion, you wait enough time that basically only the matrix element with the pion survive because all the other are excited state that have a fast decay, and then you select this. Okay. So this is really how it works. And so you understand that you can do the same thing also with another pion here, and that's it. You cannot do two pion, because two pion, then the two pion will rescatter, and so that is beyond what we can do with this type of. So these are what we call the form factor. So form factor are objects like the vacuum or vacuum pion or pi to pi. These are the easy thing, okay? This is where we don't need to discuss rescattering and all these things, and we can isolate easily from this path integral formulation, just looking at derivative. Okay? Yeah. Sorry? You mean here? Well, this is here what I meant is that something that, for instance, I can put here just a how do you call it? Here I could put, I don't need to integrate on the pion. So yeah, on the QCD side, here I will put an operator that creates the pion. So that could be, for instance, Q left, Q right. This and there, how I call it, the operator, I call it pi of x. This is external, okay? And this is something that I know that has a non-trivial matrix element between the vacuum and the pion. I can put anything. Actually, the beauty of lattice QCD these days is to build the operator such that they have a big matrix element with the state you want to create and the smallest possible matrix element with all the other states you don't want. So this way you converge faster on the state you want. It's exact, it's an interpolated field. And you have to choose, and here I can afford not to discuss what it is, because then I know that drop and there is this is the only low energy intermediate state that is there. All the other are higher static states, so I don't care. Okay. Okay, good. So that was just a parenthesis. And I did all this because the final things I wanted to mention here is indeed finally to find a physical interpretation of this lambda tilde. Now you've seen David's lecture this nice relation is that the mass of the pion is equal to this lambda tilde let's say K plus MS plus and so on, right? So this lambda tilde is really my B0, okay, the same thing. And so I can do the same trick here, and now if I take my functional, which depend on S, and then I do a derivative with respect to S, and I set S equal to 0. So in this case, really, I have a vacuum matrix element of what? Sorry, I don't set. I set S equal to. I set S to be the identity, which means I couple a universal term to Q bar Q. Okay, so indeed, what I will get when I do this functional derivative is simply Q bar right, Q bar left plus Q bar left, Q bar right, because I have the other term coming from S dagger. So this is just Q bar Q. So see the functional derivative with respect to this S gives me the expectation value of Q bar Q. Actually, this is our leading term, the one we assume to be non-zero, to a spontaneous symmetry breaking of chiral symmetry, right? Now this, if I compute it with my Lagrangian, okay, now this is very simple. Now I do the same thing here. I equate it with the functional derivative now on the chiral side. Here, I have to take U to be the identity because I'm looking at the vacuum, so I simply have what I get. S is sitting here, okay? So basically I get F squared, or F, sorry, I continue to make mistake. So this is 4. I don't know why I put 2. Apologies, okay? Factor of 2 are always plotting, but okay. So this factor is F pi squared divided by 4. Then I have these two terms on this here, chi is equal to this minus 2b0. There is a minus. We put the minus not by chance, because indeed we want this Q bar state to be negative. And I have the 2b0 from the 2 chi, which I set them to be equal. Then there is 2 because there are 2 chi. Sorry, there is a 2b0 in chi, and then there are 2 chi. And then there is a factor of 3 because of the trace, right? Because we are in 3-dimensional. For NF equal 3, there is a factor of 3. So what I get is just, okay. So you see that this parameter B0, which is equal to this lambda. This B0 is nothing but is the vacuum expectation value of QQ bar. Okay, so it's a minus 1 over. So now we have this nice interpretation of the two leading parameters, F and B0, which appear in our chiral Lagrangian in terms of two well-defined expectation values. So one is so these are really the two leading parameters controlling these are order parameters of chiral symmetry breaking. So B0 being non-zero it's because of this quark condensate is non-zero, and this trigger the spontaneous breaking and give rise to the mass of the pions. And again, this, I think, interesting alternative approach. People were thinking, oh, maybe this is accidentally small, and then there are other contributions to the pion mass. Okay, now we know for sure this is not the case. This is really the leading trigger of spontaneous symmetry breaking. And to connect, so you see, Carrier perturbation theory is also a non-perturbative EFT. So it's based on some non-perturbative assumption that there are these things which we cannot compute. It's non-perturbative, it is there. But the nice things, or for the virtue of Carrier perturbation, is that once you make these two non-perturbative assumptions, what is F pi and what is P, then all the rest, then we have this defines the vacuum of the theory, which is a non-perturbative vacuum, non-trivial. But then this vacuum is Lorentz invariant, so it's really is constant. Therefore, our effective theory is a relativistic QFT. So then we can use all the advantage of relativistic quantum field theory, which make it, in a sense, easier, more closer to particle physics than the non-relativistic one, where, of course, you have to do, or the effective theory, where you look at specific system where you have a certain other, for instance, bound state and so on. So that is the difference of KPT with respect to these others. Okay. Okay, good. So that's finish the discussion about the starter. So now we really want to go beyond 3 levels. Yes, please. No, it's not necessary. So this is I put it here just to get B0. Okay, because this way B0 is positive, because I know that this is negative. Okay. So if you want, absolutely, very good. So mass positive is positive, exactly as it was discussed. So why is positive now? You see, because this vacuum expectation value is negative. Okay, that is nice thing. So this way, putting there this minus behind you do it such a way that B0 is positive, and that is yeah. How do you know this? Well, it's yeah, because otherwise the ground state, if you want, this is defined with respect to the ground state without no, without field. Yeah, would be zero by default. Yeah. Sorry? The gluon, you mean? Yeah. Now, here, this is totally non-perturbative. There are infinite gluons. I mean, this is just a representation of this operator, okay? That is, so on the ground state of our theory, this operator get the vacuum expectation value, which, I mean, this operator, then you can rest with many gluons, so it's complicated. Okay. Okay, so let's move on with the. So now I can really connect to what David was saying about the quantum correction, okay? Yeah, that's a good question. Does not need to be a priori, doesn't need not to be. In practice, we see that it is, okay? Otherwise, we won't get that relation. So that we build the theory assuming that it is, and actually, well, where is it? If it were not diagonal in flavor, you would break to a different group. So the fact that, you see, we break SUN to SUN left plus right, which means or V. So these things means that okay, clearly you are diagonal in flavor. Now, he did this, we discussed it with a few of you during the coffee break. It's interesting because indeed, you have to assume that the ground state is symmetric in flavor and isospin to do that. Interesting, the quark masses are not symmetric on that. So one could think, oh, maybe the quark masses could have triggered a different vacuum. No, okay. What we see is that this vacuum is invariant. One reason one can, there are theorems, okay, show you that actually this is really if you have done a breaking along a different direction, you can do it, okay? In a generic, suppose you take a different theory, you can build a potential such that you do a breaking. Well, if you just play with potential, okay, toy model of QCD, then you can see that there is always a minimum here. This is a general theorem because this is the maximal subgroup of this group here. So what do you mean maximal subgroup? So this is a subgroup, okay? But you cannot build any group bigger than that, which is also a subgroup of that. While, for instance, if I take one direction as a spin, then I can build a bigger, so it should be, for instance, some U1 here. The U1 will be contained under that, okay? So will be not the maximal subgroup. So maximal subgroup are always minima of the potential, is a general theorem. So it's a very robust property to have a minimum here invariant rather than on a specific direction. Well, that is, I think in general, it's not obvious that this is the global minimum. Like QCD is this, and now this is proven, if you want, by all these lattice calculations. So there's no doubt about that. A priori, in general terms, doesn't need to be the only minimum. Then, well, no, because this is again all the experiment were already clearly showing that indeed isospin was a good symmetry. So I think nobody claimed that there was a different type of vacuum. The only thing that people claim is that maybe the leading breaking term is not the quark condensate, but some higher order operator. So maybe one can build a bit of a dot construction, which is not totally crazy, where the leading term, for instance, in the pion mass comes from the quadratic terms. Then the leading operator is not Q bar Q, but is Q bar Q square or something else, okay? This is, again, we don't know which is, of course, this will require tuning, okay? Because this is the operator of lowest dimensions. It's natural this there, okay? Again, this also now is disproven. Okay. Yeah, so for the questions, let's now go with we want to go beyond lowest order. Actually, this is the title of my lecture. So let's first do the naive estimate of what one expects. Again, this David already told you, but let's look at it more closely. So now if I take my theory, okay, for instance, I can compute something like this, which, okay, this will be a correction to pi scattering, okay? And we know that, for instance, if I take my, let's say, pi plus, pi 0, this one I computed with my Chiral Lagrangian here. I have to expand this term to 4 pions, and what I get, I think I have, maybe I have here an explicit result. Yeah, this, if you want, you do this calculation, okay? It's really simple. You take your Lagrangian, you expand it, and you find trace of the mu phi I this is Lagrangian plus terms with more pions or less pions, okay, but this is the term with 4 pions. And then you compute your amplitude, and you get for pi plus pi 0 go to pi plus pi 0, 1 over pi squared, because so this is one over okay, very simple, nice result. That, as expected, has all the properties you would expect. So with this, like 1 over f squared, because we start here with this f square. U, maybe I should have written here. U in my notation is E, and my f is the same f that David had, 92 MeV, while my pi is only square root of the difference with respect to its it's like this, okay, in terms of notation. So then we can try to estimate these things. Let's do a very naive estimate. Okay, here we have a loop momenta, so this will be an A a correction to the amplitude coming at higher order. I don't want to do the full calculation now, I just do a naive estimate. So here I have these vertex, which are of this type. So we will have 1 over f square because of the two vertex. The two vertex carries momenta, and then there is also an integral. Let's do it for the moment in 4 dimension. And there are the momenta coming from the two vertex. I put here very naively, and then there are the propagators. Really just it's a sketch, okay? I just want to understand how these behave in power of P. You see here, I have the propagator brings, each propagator brings power of momenta down, okay? Then there is the loop integral, and then there are the momenta at the numerator because of the vertex. So clearly this scale like 1 over 16 pi square, f square, sorry, f to the fourth, sorry, f to the fourth, yeah. And something which has to be of the order of e to the fourth, because it's compensated with that, and then will be some log of p squared divided by, because this is divergent, okay? We will have to introduce a counter term. And it is interesting to see how this, again, this is just naive NDA, naive dimensional analysis, how these compare with respect to the leading order result. So this I can write it as maybe I write it as A2, which scale like p squared f squared. So I factorize this factor here times my correction, which is 1 over 16 pi squared f squared. And then I have p squared and eventually the log. You see, this is the naive size of the correction I expect. Okay? And that's why David would say, look, the naive suppression of this diagram, so I have momenta here and I have this scale. So this I can define this scale lambda chi, which is 4 pi f, which seems to rule the suppression in the momentum expansion with respect to lowest order. So this is 1 GV, which is nice. So it means that if I do pion physics, and I have pi scattering where the invariant mass is of the order of the pion mass, maybe 4 times the pion mass square, still I am way below this cutoff. It actually did turn out to be, this is indeed somehow the correct cutoff with the, and also this is, well, with some caveat. In some cases you have something slightly higher. Of course, there are order 1 coupling, which, however, one can interpret well when we have, for instance, production of resonances. When we have the row exchange, when we have a channel where these two pions can form a row, you will see actually here what appears is really more the mass of the row. And but it's a, okay, before going to calculation, so intuitively, yeah, we have this theory where we have this 4 pi f, or 1 GV, where really here is a mess, okay? It's complicated. Then we have m pi or 2 m pi, which is what we, this is the range where we want to discuss scattering length, which is really well separated from that. And also, since the expansion, we'll see it's quadratic the momenta, the naive correction you expect, the naive expansion parameter you expect for scattering length is for pion scattering length, it's 4 m pi squared divided by this lambda chi squared, which is very small, at least it's 6%. The count mass sits here, a bit higher. So for instance, for count decays, the expansion will be mk squared divided by lambda k squared, which is still reasonable. This is now it's 25%. But just for chaos decays, not chaos scattering, okay? It's very for chaos decays, the energy will be the chaos mass or below. So actually the product of the chaos decay are pions and the rest. Then there are these interesting, so clearly this somehow is where we stop. But what is interesting, we'll discuss it tomorrow. Yeah, the fact that here there are not many resonances between here and there, so there is resonances that are coupled to pions, so there is only essentially the vector mesons. These offer an interesting way to interpolate between these. Finally, here, this is really the things where we need lattice or anything else or something else. And finally, here there is perturbed by QCD. So these guys here seems to be playing a very important role to interpolate between here and here in terms of properties of our green function. And we'll discuss this next time. So finally, the last things to proceed now with the loop calculation is, I think it's worth in Kerr perturbation, we can really do a proof that the loop expansion works, because which is not completely obvious. You see, this theory contains, it's a theory that if you look in terms of pions, contains an infinite number of operators already at lowest order. So here, this term, when I expand in the pion field, I have infinite term. So it's a theory where, yeah, the operator written in that form, and this is the power of the symmetry, just one. But if I count how many type of interaction term I have, it's infinite. So you have 2 pions, 4 pions, 6 pions, anything, okay? Or if you put external sources, also odd power pions. So, it's interesting to understand if the number of counter terms is finite, okay, and how it's scaled with respect to the loop. This is a nice argument that was given by Weinberg about the power counting. So which is the level of power in momenta that we expect from the loop expansions versus the one that we have from the higher order operator. And so the tricky thing is about the loops, no? So this is obvious that this loop brings something which is of order p to the 4th, okay? So which is something which will be cured by a term with 4 derivative in the Lagrangian. That gives p to the 4th. But generically, how it works. So here there is this nice loop counting argument, which goes as follows. So suppose you take a generic loop with arbitrary number of interaction, okay? Anything, whatever. Now, for any loop, independently of the theory, there is this nice relation that the loop, okay, the number of loop is equal to 1 plus the number of internal lines minus the number of vertex. And this, I think, is something easy to understand. So it really doesn't depend on Kerr perturbation theory, right? Okay, let's check that. So clear that, okay, here, clearly, first of all, the number of external vertex do not matter, okay? The only thing that matters, so this is why I do it with blocks. What matters are the number of internal line and the number of vertex. So for instance here, if I add a vertex but not add an internal line, clearly it's still one loop, right? So this is why I have internal line minus vertex. On the other hand, if I add a vertex that something like this, then here I add the vertex, but I added more internal line. So then you can easily check that this relation holds. So if I add vertex but not internal line, okay, I don't change the number of loops. While if I add more internal line than vertex, then I enhance the number of loops. Okay, this is a general topological formula. Now we want to apply to our KPT result, to our KPT structure. And so we want to understand the degree of divergence of a generic loop in KPT. Actually, this loop, we don't have it in KPT because we need, well, we'll have it something like this, right, for instance. So which is the level of divergence. Let me call it n. So not the level, sorry, the power in momenta that I expect from a given loop amplitude, n. So each loop, okay, when I have a loop, this carries a integral over the loop momenta, which is, if I do in d dimension, brings d power of momenta, right? So if I do a loop integral here, I have actually this, I could have done it if I do in d dimension. This brings this power of momenta at the numerator. Then I have to count there will be power of momenta at the denominator, which on the other hand depends on the number of internal lines. Each internal line, for me, these 4 momenta are only pions, so each internal line will be 1 over momenta squared, because it's 1 of p squared, right? So then I have minus 2 times the number of internal line, and then I will have positive power of momenta by the, sorry? Then I have the power of positive power by the vertex. And here in perturbation, in Carrier perturbation theory, I will put different vertex with different momenta. So I write it like this. I know that I start from our Lagrangian L equal 2, but generically I will have L. So generically my Lagrangian will be sum over k L to k, because I cannot write Lagrangian with an even number of derivatives with only pions. So this starts with 1 and goes to infinity. And so we have k equal 1 is L2, k equal 2 is L4, and so on. And this one contains vertex with a power of momenta, okay, of order p to k. Okay, that is what is written here. Now, okay, this is, I have not used that relation, so now let's use that relation here. And I use it expressing, I think, what I want to use express the number of internal line versus the number of loops. So I have L minus 1 plus V. So I have L times T minus 2 I, sorry, I'm a bit late, L minus 1 plus V plus sum over K actually V is the total sum of vertices. Actually, this is sum over K okay. And now I can reorganize all this. So I have, from here I have a 2, plus I have loop that multiply d minus 2, plus sum over k that goes from 1 to n, v to k, and here I have the 2k, but also I have a minus 2, so here I can put a 2, and here I have k minus 1. So that is the counting, and it's nice because it's telling us, you see, first of all, that this, okay, this is 2 is positive. Okay, we want to go into 4 dimensions, so this will be positive. So this will be in d equal 4 will be 2L, which means any loop will add momenta, no matter what. Okay, so if you add a loop, you add momenta. And also here is these interesting things. If I take k equal 1, which means insertion of L2 brings no extra power, which means I can use my L2 Lagrangian how many times I want. So insertion of L2 do not cost anything in terms of extra power in momenta, because whenever I put it, then I put the propagator, will compensate, will be cost 0. On the other hand, any other insertion will add. Okay, and then we end up with this simple table. So order in the expansion. Okay, then we have to see. So if we start at order 2, we have loops L2 and L4 and so on. So loops, no loops, any L2, no counter term, nothing. Okay, that is what at order p squared we just have to put L2. Easy. Then when we go to order p to the 4th, on the other hand, we have, if we put one loop, okay, I'm already saturating this, which means then I still can put any of this, but then I cannot put the counter term. So the counter term, which again you would expect, but I cannot put the counter term and the loop at the same order. Okay. On the other hand, if I don't put loop, then I put one insertion on L4, and this will be at the same order and will cure my divergence. Okay. And again, this is any. When I go to P6, things becomes more complicated, and people have done it. So people have computed pipe scattering out to order P6, and then you really see this beautiful convergence. I will show you the result tomorrow. So here you see that there is, if I can put two loops, again, any, nothing here. I can put one loop, this is always anything, and one P4. So at all the P6, I can consider loop with there is the P4 insertion in the vertex, or finally I can have no loop, and then I have my P6 Lagrangian appear. Okay, then you can continue. But clearly it's a systematic, number of terms increase, but in a systematic manner, and there is a nice, easy power counting. So in particular, at order P4, we have the loop, okay, with any L2 insertion, plus single insertion of L4. Okay, so I think this is, should I stop now? Yes. Okay, this is a good point to stop, and then next time we really then look at the P4 Lagrangian and all its, glory. Okay. Okay. No, this is I didn't discuss divergence. I just discussed the consistency. Sorry, good question. Because I started saying divergence. No, I don't discussing for the moment any issue about divergence. I'm just discussing the power counting, which is, however, you remember yesterday the key ingredient for NFT is first of all power counting. So this is the consistent power, so which means the divergence which I get here will need to be absorbed here. And again, tomorrow we will see really the generating functional at order P4 with all the operator. And what I also sketch how I compute the anomalous dimension of this term really in a currently invariant way that will cancel completely the divergence. Okay, one can really prove, this is the nice thing in current perturbation theory, because being a relativistic, you can really prove that divergence cancel at the functional level. You can really compute exactly the structure of the divergences. You can show that these correspond to local operator or P4, and then this way you also identify the anomalous dimension of this operator. So the game is close. Yeah. That's a very good question. Yes, very good question, which we did. I didn't discuss. Indeed, one should establish the power counting for the sources. Yes. Now, here, for instance, for R and L, this is kind of obvious because it appears together with this. So we will assign automatically power counting P to L and R because it appears together with this derivative. Okay, so this is the natural power counting, and there is little to discuss about that because they have to appear in this form at the lowest order to compensate. So this is clear. For the masses, again, it's not obvious, okay? In practice, since this term will generate the pion mass square, and then pion mass square, you get it by the equation of motion as P square, the natural counting in this to assign to this chi also power counting P square, because we'll generate this, when I put it here, this is correspond to the pion mass square. So this will count as P square. Well, because of the equation of motion. So for a non-shell P square on shell is equal to M square. Okay, so when I close my kinematics, this has to be like, this relation has to hold. So this count as P square. Yeah, exactly. But then we will also use kinematic relation in the closure, and so this is why we count M square of order P square. Indeed, this alternative procedure that was proposed is called generalized chiral perturbation theory, which now people have completely forgotten, was assuming a different counting for not really for the mass. So the mass square that you get from kinematics, this has to be like this, okay? But then you can do a different counting for really this object here. So you can put here chi and chi square and give a different counting for this term. So then assume that the pion mass is dominated by chi square rather than chi. Okay, that was a possibility that now is ruled out, but was possible. Then when we introduced also the, also David already showed you how to introduce the electromagnetic when we have the photon loops, no? When we have the photon loops, indeed, I have to introduce something else, which, okay, David already showed you, this Q left, Q right charges as breaking terms. And also when we introduce weak interaction, we do something similar. There again, I have to define my counting. For instance, for the pion, the correction to the pion mass, you see that the operator that was introduced is similar to this one with Q, okay? Very similar. Well, it's, you've seen it maybe. It's this operator of the type, yeah, so this one is right. Sorry. Yeah, this operator, right? This operator has no derivative, okay? So here, but then you put E square. So actually here, what really gives you the counting, in a sense, you forget, it's E square. So actually this operator, we call it E to E square E0. So there is no momentum, but there is E square, okay? And actually this is a different counting, okay? I cannot really mix with the normal. So while all the other operators which I was considering there were E0 e to the n, okay? And then you can do, then you can go to O E square, E square, and so on. And then you have a double expansion. And that, depending on what you want to look at, you have to choose. Okay, maybe it's time to stop. Good.